Yes. So today I'll talk about collapse transition of a charged polymer. This is work done with Andy, who's a student at Math Science, Vani, who is here, and a brilliant talk from Leicester. So it is well known that if you take a neutral polymer and put in solution, depending on the nature of the solvent, it can be extended, it can be collapsed, and in between theta solvent or something where it undergoes one transition. A good solvent is one where the polymer, the monomers in the polymer prefer interacting with the solvent, while the poor solvent is one where the monomer interaction is more dominant than the monomer solvent interaction. Now, this transition is quite well described by the Flory theory, which consists of writing terms, an entropy term, a second virial coefficient, third virial coefficient, and so on. And when the sign of this virial coefficient changes, the polymer undergoes a transition from extended to a collapsed phase. Okay, now what happens if the polymer is charged? So this diagram is a schematic diagram of a charged polymer. So if you put a polymer in solution, often what happens is it loses ions into the solution, making the polymer the backbone charged. So one could think of it as charges plus Q along the polymer backbone, and the negative charges in the solution. It could be, for example, a divalent compound in which the charge is twice the monomer charge. So a polyelectrolyte is an overall neutral system, but the polymer by itself is charged and the counterants are in the solution. Now, the conformations of this polymer depend on the charge density that is put in, and that is characterized by something called a theorem length. So what you do is you take two nearby charges along the polymer backbone. You ask what's the electrostatic interaction at the neighboring two monomers, and is it comparable to thermal energy? If LB is very small, which means you can ignore electrostatic interactions, and if the theorem length is very large, the electrostatics become important. No. So when I call it non-dimensionalized theorem length, sorry, it's non-dimensional. So normally there's no B. I put it is non-dimensionalized. So to illustrate the behavior at small, intermediate, and large density, I'll just show three movies. So at small theorem length, the counterions remain in the solution, and the polymer behaves as if it's a neutral polymer. Then, if you increase the charge strength or the theorem length, what happens is the counterions start condensing onto the polymer. It's called Manning condensation by some procedure called Manning condensation. And then a certain fraction of the counterions condense onto the polymer, but the polymer is still extended. Now, if you increase the charge strength even further, look at larger theorem length, then all the counterions condense and the polymer collapses, okay, just like the neutral polymer. So you have this transition from a extended to a collapsed phase. So the question I'd like to ask is, what is the origin of this attractive interaction that drive this transition? No, you have a nice transition. Which one? So here there's a critical LB beyond which undergoes a transition from extended to a collapsed phase. Yeah, that's encoded into the LB. Okay, so that non-dimensional number has both these factors put in. It has the charge comes in there, the temperature also comes in there. You can drive it either way. Yes, but no. So the barrel length he's talking about has no is dimensional full, I guess. In the non-dimensionalized sense, it doesn't matter. This parameter drives it. No, right now this is the generic one. When I come to what we do, I'll tell what the polymer model. So why study this question? Most biopolymers are polyelectrolytes. DNA, actin, microtubules are examples. So understand the nature of attractive forces seem important. So there are quite a few theories for this. The most commonly accepted one is a dipole theory, in which it says when the counter ions condense onto the polymer, they form fluctuating dipoles, and fluctuating dipoles effectively create a van der Waals type attraction, and that modifies the second virial coefficient in the Flory theory, making it negative, and it drives a collapse transition. Then there is another theory called counter ion fluctuation theory, in which the counter ions are treated as a plasma, one component plasma, and charge fluctuations in this one component plasma create an effective attraction. And then there's another one called ionic solid, in which the counter ion and the monomer make a solid ionic bond. They don't fluctuate anymore, and that there's an effective attraction due to that one. And there are more theories like that. All of them predict a collapse transition. But what I like to figure out is whether there's a more quantitative prediction which can be tested. So it turns out there is one, and that is a prediction for the radius of gyration, Rg. So it says that in the collapsed phase, these theories predict different scaling relations, scaling power laws for the radius of gyration with theorem length. Okay. For the dipole theory, it says is Lb2 minus 2 by 3. This one says minus 1 by 2, and this one says Lb equals 0. The question is, can we test this out and rule out one or the other? Now, so what we'll do is we'll use molecular dynamic simulation to test this. So a priori, it's not very clear whether these small differences in exponents can be found out using MD simulations or not. So this is the main result. So what we do is we create a bead spring model for the polymer, make it charged. The counter ions are treated as spheres. So in this particular plot, we use Lennard-Jones interaction, which are completely repulsive. The attractive force is only due to the charges. This is the germ length, and this is the radius of gyration. This is scaled by the germ length at which the things collapse. Now, for small germ length, we find a scaling which roughly goes as 1 by root LD. But for large germ length, they find it goes as LD to minus 1 by 5. This is no, the edge interactions are completely repulsive. We treat them as spheres which repel on contact. So the no repulsive polymer. Gaussian is bond and angle, yeah. But we are treating a flexible polymer, so there's no angle interaction. No. So this minus 1 by 5 we find here is different from all the three predictions here. So, so that is my main result. So it says the scaling exponents are different from the predictions of all the theories. However, so we like to ask whether maybe one of them can be modified. So we can modify the one component plasma theory to add more terms, and that actually reproduces scaling for both small and large LD. We can give you the crossover too. And then, of course, you can make the simulations more complicated. You can add a solvent, you can make it poor solvent, and things like that. And all of them are consistent with this modified theory. And so yeah, we have a lot of time. So these are data for monovalent, divalent, trivalent.
Oh, here. Okay.
And the inset shows that it doesn't depend on the system size we use, so it's not.
Because it's known that for Manning condition, the multivalency they also make difference. The counter and fluctuation and the.
Yeah, but here we find that all the curves lie on top of each other. Once you scale with so this LBC depends on the valency, but once you scale with that, they seem to be independent of valency. What is RPM? I don't know. It should not, in my opinion, it should not, I don't know what this model is, but we have looked at explicit solvent. We have looked at interactions which are more soft, and all the curves look exactly the same. They don't change.
So what is the interaction between this polymer and the charge was not very clear. What is the, like it comes and each bead has a charge that's stick to the polymer.
Yeah.
And then there are some counter-ions in the medium.
Solution.
Okay.
And they come in contents.
And just the Coulomb interaction.
Yeah.
Okay. And even within the polymer also they interact? Okay. Why do you need this LJ interaction? Why do you need this
interactions?
LJ repulsion? Because anyway
you don't want it to fall on top of each other.
No, but anyway you have this two same charges on the polymer, right? They will anyway repel, no?
No, because of the size is imposed by putting a repulsive interaction.
Okay. But even the charges are the same kind, no, on the polymer?
No, they won't come nearby. But if you don't put a repulsive force between the monomer and the counter-ion, they'll just come and sit on top of each other.
This is between this interaction is what? Between different beads?
Between beads and the counter-ion also.
Ah, okay.
Yes. Effective size for them. Yes.
Yeah, so radius of gyration varies as n to the power 1/3 in all the three phases.
No. This data is only for the collapsed phase. That is why this 1/3 is put here.
I see. Okay.
Here, the intermediate phase, like this one, it is not very clear. In the literature, they would say this scale says N. But if you look at this plot, I would say it should go as a self-forwarding walk. But if you look at large enough N, you should look at it go as a self-forwarding walk. Because
the extended phase, it varies as L or not even there?
In this one? Here, it should be a self-forwarding walk because the charges can be ignored and should behave a neutral polymer. But if you look at small system sizes, it looks very rigid. So that is the point. So this transition from here to here, from this phase to this phase, in the usual neutral polymer is a continuous transition. But here the predictions are all first order. But we have not been able to check this out very clearly. No, this is salt-free. Yes. No, of course, we can think it to be from that, yeah. Oh, no, you have to include in the, since we are having only repulsive interactions, if I look at the Flory theory for neutral polymer, you can truncate at V2 and get the right answer because V3 is not relevant for that. But in this particular case, when the attractive forces become large enough, the third virial coefficient, fourth virial coefficient, they all become dominant. So if you include some of them carefully, then you can match all the exponents well. No, it is completely flexible.
I see. If you take semi-flexible, then what should happen? I mean, still the healing, etc. be valid?
Ideally, if you include semi-flexibility, it creates a persistence length beyond which I would claim the thing goes off.
For large,
yeah, but you can form structures which are not really spherical. You can form toroidal structures. So I'm not very sure what will happen. No, that was just.
Okay, so if there are no more